This is another issue. Okay, so today I'm going to talk to you about the basics of queuing theory. How many of you guys have taken stochastics? Or are taking it now? Oh, I see a friend. Yeah. Okay, so a lot of you are taking the class now. This is the topic we cover at the end of the semester in stochastics in much greater detail. But for now, we're going to give you some very basics of queuing theory so that you guys can understand kind of what's going on in your simulations. And this more or less set the foundation for why we do simulations. Because what it ends up happening is a whole mathematical branch called queuing theory was developed, but it only worked for very basic processes. And when life got difficult and complicated, it no longer worked. And so we need to do computer simulations. But with that said, there is still some value in understanding some of the math behind what's going on. Okay. So what is queuing theory? Well, basically, queuing theory is simulating what happens when we have some sort of customers or entities that are going to be processed by a server. So the very prototypical example is customers at McDonald's sort of waiting to be served by a cashier. Another very, very good example is in telecommunications. Actually, that's where most of queuing theory comes from, is from the very, very early days of telephones. Because, what was that, like 100 years ago or so, I think? I don't know when Graham Bell did his stuff. But back in the day, there used to be a switchboard operator. And one of the big questions that cities had when they first started setting up their, their switchboards is, how many operators do we need in order to take all the incoming calls? So how many of you guys watch, what's that TV show with the comedian in the 50s or 60s who's a woman? Mrs. Maisel. Yeah, so if you remember one of her first jobs, she's a switchboard operator. So I don't know if you guys have ever seen what that looks like, but it is, oh, cool. Let's see if we can see a YouTube video. But literally what's happening is a phone call's coming in, and the operator picks up, and they say like, hey, who do you want to connect to? And the person will tell them, hey, I'm Bobby, I'm trying to connect with Susie. And what they'll do is they'll actually take a wire and plug it in to a line that goes directly to Susie. And so what you see is them plugging in cables back and forth to connect two parts of a circuit, which is like absolutely wild. And so one of the big questions is, how many of these people do you need to work at a switchboard? So this was really where queuing theory got developed. So these guys like Erlang and stuff like that, they were all dealing with telecommunications. Okay, but that said, nowadays it gets used for a whole bunch of other things. So we can talk about amusement parks. Like we use queuing theory to figure out how long people wait in line for a particular ride maybe. Or hospitals is a very, very big area where we look at the flow of patients through an emergency room, whether that's check-in, triage, seeing a nurse, seeing a doctor, going to getting your diagnostic tests to be run, okay? But really we're talking about two parts when we're talking about a queue. The first one is the server, and the other are the entities that are going to be processed through that server. Okay. And so, in fact, we can be a little bit more complicated about it. So normally when we're talking about a queuing system, it gets characterized by 4 different parameters. And so those 4 parameters are sort of written out right here. The first one is the arrival rate. Okay, so these are how quickly are customers getting into the queue, okay, or whatever system you're talking about. So how often are customers arriving at the hospital? How often are guests arriving at a ride at Disney? Stuff like that, okay? So that is our inter-arrival rate, okay? And so, yeah, that's the inter-arrival rate. The next piece of information that's very important when we're defining queues is the service rate. So how quickly can a cashier or a doctor or even, we could say, a university, so there's a fun problem, how quickly does each one of those entities process, each one of those servers process an entity? So how long does it take for a cashier to take your order and put it in? 1 minute at McDonald's, right? They're pretty quick. Okay, so that refers to the service rate. All right. Another thing that's kind of important when we start talking about queuing systems is the number of servers. Okay? So typically we might think, okay, a service queue has one server, but there are certainly examples where we have multiple servers and one line. So an excellent example of this is when you check in at the airport. Right? So when you walk into the airport, everybody gets into one big line, and then you have a bunch of ticketing agents, like 5 or 6 ticketing agents. In that case, you have a single queue with multiple services, right, or servers, which are these guys. So when we have the multiple server version, we see, here we have 3 servers, but one line. Okay. All right. Lastly, the 2 other properties that we often talk about when we're talking about queuing systems, one of them is the maximum length we allow this queue to get. Real world application, why might we limit how many people are allowed to be in a queue? Capacity. So a good example of this is, I'm pretty sure any restaurant you've ever gone to says something like maximum capacity, 100 persons, right? There's some fire code reasons. So that's a good one for a physical capacity. Can anybody else give me the electronic version of a physical capacity? Server capacity? So processor capacity is tied to the number of servers you have, right? So if you're into computers, these are like cores on a computer. Okay? What about the queue? Not quite. Close. You guys are dancing around it. So when you buy a computer, what do you care about? CPU, RAM. Right, what's RAM? RAM is like your temporary memory. Yeah, it's you have your hard drive space and you have your RAM. So what's happening is the RAM is like little bits of information it's storing that in its quick recall memory that's going to get processed to these servers. So if you're talking about like database, or not database, routers on the internet or switches on the internet, sometimes these switches only have so much memory in order to store packets that are getting communicated through a network. And so in this case, the amount of memory limits the size of the queue. So if you ever see an error that says something like buffer queue overloaded, that's exactly what we're talking about. Okay. So you guys might not see that, but it certainly happens. Okay. But usually in industrial engineering, we deal with the physical capacity of a queue length. Okay. Another good one is even telephone lines. Like, have you ever called in? Maybe it doesn't happen anymore so much, but if you call into Ticketmaster and you can't even get a pickup, they'll say something like, "I'm sorry, this telephone number is overloaded." Right? Same idea, right? There are only so many lines that can go into Ticketmaster, and after a certain number of phone calls, they just can't handle anymore. All right. For those of you who like hacking and stuff like that, that's what a denial of service attack essentially does. Right? If you send in so many requests to a server, it gets overloaded, and it doesn't know what real requests are or not. So, but that's sort of an aside. So one of the other things that defines a queue or a queuing system is the service policy. Okay? So that means as people come into the system and they join the line, how do you decide who gets processed next? So the most common method that we use is called first come, first serve, right? So this is typically what we call most fair for most people. There's another one called last in, last out. Can anybody think of where you have last in, last out? So the last thing that comes into the system is the first one that gets processed. It happens. It's kind of rare. Any of you ever work in a restaurant and clean dishes?
Yeah, 2 minutes.
Not quite, maybe. Oh, yeah, kind of. But usually people think of it with dishes, right? So like, if I'm cleaning dishes and the busboy starts stacking up the dishes, plate, 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 the next dish that I'm going to clean is at the top of that stack of dishes. Okay, so that's that should not be Lilo. That should be LIFO. Last in, first out. Okay? So that's an interesting service policy. There are a few others. Another good one is like minimum time. Okay, so I think a lot of people do their work this way. You choose to do the jobs that are easiest and take the least amount of time, and you put off any jobs that take a lot of time. Okay, we certainly do that. That's a policy that sometimes people use. Another good one is priority. I always like telling the story about priority. So somebody told me about a KLM flight. They had a few KLM flights coming into Atlanta. And what happened was Atlanta was experiencing some thunderstorms. And they said, okay, only a certain number of these flights, these KLM flights, can land in Atlanta. Some of them are going to have to be delayed an hour or two. And what KLM actually does, which was very different from most airlines. So most airlines will just look at international flights or large flights and say, these are the flights that have priorities. All the other flights with a small number of passengers, we don't really care about. So KLM did something a little bit different when they have bad weather. Not only do they look at the airplane, they look who's traveling on the airplanes. And so there was a case somebody told me about where they had like a super diamond platinum person flying on an airplane. And they said, this guy generates so much business for our company, this flight has priority over all other flights. And so we're not going to let this one be late. Because if he's mad, then we lose $100,000 worth of business. Okay? So for that reason, they decided, we're going to delay 5 other planes, but this guy, it's landing in Atlanta. Okay? And these are all examples of how service policies sort of affect a queuing system, a determinate queuing system. Okay? Now, the way this gets encoded is using something called Kendall's notation. Okay, so A, B, C, K. All right. And we'll go into this in a little bit more detail, but a lot of times you'll see in your problems, you'll see something like MM1 or MM5. Okay? And in fact, this is Kendall's notation, and what it's saying, and we'll get into this maybe a little bit later, and you'll learn this, is your arrivals are something called Markov. Right? So the rate at which they follow a Markov process, the rate at which they're processed are Markov, and the number of servers that you have are 1. In this bottom case, we have Markov, but we have 5 servers. Now, I am missing a whole bunch of other information. So you'll notice I did not write the maximum buffer queue. And if you don't write anything, it's assumed to be infinity. Okay. Likewise, I didn't say anything about the service policy. And if you don't say anything about the service policy, you just assume that it's first come, first served. So this is a very high-level overview of what's going on. Okay. Now, when we look at these queuing systems, so right now we're talking about a queuing system as just one thing, right? So we have one server, and maybe, we can imagine there would be 4 servicers here. But one server and then a line. And that's it when we talk about a single queuing system, right? There are a bunch of properties that we might be interested in related to the performance of this queuing system. One is, how long do people wait in line on average? What is the maximum time they wait in line? Or maybe what is the maximum time in the system? So when we talk about the time in the system, we're talking about the time they spend in line, and then the amount of time they're getting spent being processed. Right? Other relevant metrics that we often care about is the throughput. So how many customers are we processing per hour? What is the average amount of time they spend in the system? Right? Or what is the average queue length of our system? Okay. These are, and the good one is the utilization. Okay. How often is this server being used? Okay. So certainly from a customer perspective, you can understand why these might be helpful, the top ones. But why is the bottom one useful? Let's say I run a McDonald's, right? And I care about the utilization of my servers, and I say, hey, the fraction of time that my servers, let's say I have 5 servers, okay? So really I have 5 cashiers working, and there's a single line here, right? Okay, and I say, hey, my utilization is 10%. Why would I care about that? From a practical perspective. Money, why?
You're paying.
Yeah, I'm paying these cashiers to work and they're only working 10% of the time. So what might I consider doing? Cutting them back, right? Unfortunately. Okay, so I fire some people. What's probably going to happen to the average time in the queue? It's going to start going up, right? And so you're going to have to do that trade-off between, customer service performance metrics and the cost of running your system. Okay. Let's say, now this is more of a hypothetical. Let's say my utilization for my McDonald's was 98%. Could you make an argument why that would be bad? Yes, sir. Excuse me? Yeah, the queue time would be very long, right? Okay, so I think we got the customer perspective covered. Why might it be bad from a server perspective?
You're overloading the employee.
The employee. What happens when you overload employees?
They get angry.
They get angry, and what else?
It's sloppy.
They get sloppy, they make mistakes. Alright? You have a whole bunch of issues related to overutilizing your servers. Okay? So don't think, hey, low utilization is good or bad. Don't think high utilization is good or bad. Don't even think 50% utilization is good or bad. In this class, most of what you're going to be doing is balancing all these metrics together and creating an argument of why you think one system might be better or worse. Okay? They just all have their features. Okay, so back in the day, we used to make you guys simulate these things in Excel. Right? And we'll sort of work through one really, really quickly. We could simulate a queue like this, and what we have here is a table where we have each customer number. This is the time that they arrived at. Okay, so the first customer arrived at time 0. Right? The next customer arrived at time 3. Right? So this third column is something called the inter-arrival time. It is the time between any 2 customers. All right, so what we see here is that the inter-arrival time between customer 1 and customer 2 is equal to 3. And we just get that by taking the difference between these 2 numbers. So if we look at the inter-arrival time between customer 2 and 3, we subtract 4 and 3, and that gives us an inter-arrival time of 1. So typically what you can do is, I don't know if we'll do this in this class with Jorge, but sometimes we'll have tables where you get the customer and the arrival time, and you'll be asked to solve for the inter-arrival time. Or maybe what you do is you get the inter-arrival times, and you have to calculate what the actual arrival time. This one's actually, this isn't too bad to calculate. All you have to do is find the difference between each rows. If you get the inter-arrival times and you want to calculate the arrival times, you just do a running addition of the numbers. Okay? So for example, the arrival time of 14 is just equal to 0 plus 3 plus 1 plus 3 plus 7. Okay? Adding that stuff up will give you 14. Okay. All right. So one of the things that we can do is we can describe the average inter-arrival time, okay? And so what we do is we take these inter-arrival times, we add them up and divide by 10. Okay, or in this case, actually, it makes sense to we add up these 9, right? Because the first guy doesn't really have an inter-arrival time, right? It's the first one. We add up all those times and divide by 9. All right, and that gives us the average time between customers who arrive into the system. If we want to talk about it in terms of a rate, what we do is we take that average time and we say, we calculate lambda, this parameter, so this parameter that we're calling this, and we talk about 1 over that average inter-arrival time. And this will give us the rate of customers arriving into the system. In this case, the average time of the inter-arrival, so if I took these numbers, added them up, and divided by 9, I get, so I'm taking average of inter-arrival, I get 4.2 minutes between customers. Okay. Again, if I want to turn that into a rate, then I just do 1 over that expected value. Okay, so 1 over 4.3. And that's in units of customers per minute. Okay. And so typically our problems, we're going to give you one number or the other. That's more or less one. Okay, so we've now described how the customers enter the system. The next thing that we're going to do is describe how customers are processed. And in this case, the way we normally describe it is by a service time. Okay? So this first customer, let's say he went to McDonald's, it took him 2 minutes to order. Right? Pretty straightforward order. Right? The next customer had a big order, so it took him 5 minutes. Right? And each customer has its own service time. In the same way, we can talk about what is the average service time of all the customers. So we add up all the times, and in this case, divide by 10. If we want to estimate sort of what is the average service rate, then we take that expected service time and we divide it by 1. Or 1 divided by that service time, sorry. Okay. So these 2 parameters are ones that we're going to refer to pretty regularly in this class. One of them is lambda. So lambda is always going to be an arrival rate, while mu will always refer to a service rate. So they're going to be 2 sides. One is how customers come in, and the second one is how customers are processed. All right. So the fun part begins when you start getting tables like this. All right. And we can start asking, well, when did the first customer begin service and when did the customer end service? And so you can actually figure all this stuff out based on the rule, the policy, so if they're first come, first serve, and what times they arrived and how long they were serviced. Okay, so let's sort of figure this out. So if the first customer arrived at time 0, they get into line at the cashier. When do they begin service? 0. Yeah? It takes them 2 minutes to be serviced. So when do they finish service? 2. All right. So customer 2 arrived at time 3. Do they have to wait in line? No. The server's not busy, right? Because the server finished with the other customer at time 2. So that means customer 2 goes right into line. All right? They begin service immediately. It takes them 8 minutes to get processed. So when do they finish up? Or 5 minutes? At 8, okay, yeah. All right, so now let's look right here at customer 3. What customer 3 comes in at time 4? Is the server busy or not? Yes. Yeah, the server is busy. How long is the server busy until? Time 8, right? Okay. So customer 3 is not going to start until time 8. What time are they going to leave? 10, right? 2 minutes later. And the part that gets really neat, so one thing that we can start talking about, we can talk about how long each customer had to wait. I think that's normally WQ. WQ. Okay. So let's think about this first customer. Did the first customer have to wait in line? Nope. Did the second customer have to wait in line? Nope. The third one?
Yes.
Yep. How long did they wait? 4 minutes. Okay. So you can keep going through this process, right, of figuring out whether the server is busy or not. All right, so customer 4, let's do this. We can fill this out pretty quickly. Customer 4 arrives at time 7. Is the server busy? Yep. All right. So what time do they actually get serviced? At time 10. They end 3 minutes later at 13. That means they waited 3 minutes in line. Okay. Customer 5. What time do they enter? 14. Do they go directly into line or do they have to wait? They go directly in. Okay. They arrived at time 14, but the previous customer finished up at time 14. Or 13, sorry. So we can keep going through this process. 16. So customer 6 arrives at 16, but the previous customer just finished, so he slides right in. Gets out at what? 23? All right. Next customer arrives at 19. They're going to have to wait until 23. All right. They're going to leave at 26. That means they waited 4 minutes. All right. And we can keep going through this process, right? So you can imagine then, you could actually calculate if I gave you 100 customers or 1,000 customers or any number of customers, you could calculate what is the average time that people waited in line. So not only can we calculate the average service time or the average inter-arrival time, we can calculate meaningful statistics about how long they wait in line, or what is the maximum observed time in line. Okay. Now, a lot of times we're going to make assumptions about how customers arrive. Okay, so what are these inter-arrival times and what are these service times? Okay. And one of the things that we're going to do in this class, and queuing theory does, is they assume that the inter-arrival time between customers follows the same distribution. Okay? And this is referred to as IID. Okay? So this is IID. And IID stands for independent and identically distributed. Okay, so what does this mean in plain language? Let's say the time between the first customer and the second customer. So let's say it took me 5 minutes. For 2 minutes, 3 minutes, doesn't really matter. The time between two customer arrivals has nothing to do between the time between the 100th and 100th person who arrived. Okay? Those arrival rates or arrival times are independent of each other. Now you go, okay, that seems kind of weird, but maybe that makes sense. Why would you make that assumption? Well, that assumption isn't particularly useful, or at least meaningful, but you'll take it. But it starts to make more sense with the service time. So if I say service times are IID, what I mean by that is the amount of time, let's say it takes me, the first customer to be serviced, is independent from the amount of time it takes Jorge to be serviced, right? Or maybe Jose to be serviced, right? Or John to be serviced, and Sarah to be serviced. They're independent of each other, but they're drawn from the same random distribution. Okay. So what's the converse of that? Well, the real world, so we make this assumption, this IID assumption, that the time it takes to be serviced by a queue is independent and identically distributed. Just makes the math easy. Okay. The converse of this is that, let's say I get to McDonald's and I order some huge order. What's going to happen to the worker maybe? and I'm a jerk about it, right? What's going to happen to the worker? They're going to what? Get confused, get upset. Maybe they've been working a long day. All right. Let's say I just put this worker in a real foul mood and they can't concentrate. What's going to happen when they service floodhead? Are they going to take the same amount of time they might normally? No, they might take even longer. All right. So in the real world, this IID assumption doesn't always happen. All right. We're assuming that the time it takes to service me is independent of the time it takes to service floodhead. But in the real world, sometimes they do depend on each other. All right. So a good one is, just sort of generally, the longer in the day somebody is working, typically, the slower they work. So this is the IID assumption. Okay. Now, I think I mentioned a couple other assumptions that we talk about. The first one is that we typically have an infinite buffer. Okay? Because the math doesn't work out if you pass it out. It makes it really hard. One of the other ones that we talk about is having Markov arrival and Markov service times. Okay, so So whenever we have a Markov service time, okay, Markov service time, service, yeah, okay. What we mean by that is, let's say here goes a PDF. Right? So this is time, and this is the PDF function, f of t. What we mean by that is that the time it takes for any customer to be serviced follows an exponential distribution given by lambda e to the minus lambda t. So hopefully you guys remember this from probability statistics. This is a fundamental property of queuing systems. And again, we'll study it a bit more in stochastics. But this basically tells you how likely any value of service time is. So you're kind of more likely to have shorter service times over here than you are to have a longer service time over there. And so when we say we have Markov service times and Markov arrival rates, what we're saying is that the time between arrivals follows this equation, and the service times, or the probability distribution of service times, follows that equation. All right, so it's not, a lot of times I think most of y'all are used to working with like normal distributions, right? That's not what we're talking about here. There's a different probability distribution. Okay. And in fact, this parameter, lambda, is exactly the one we were referencing earlier with the arrival rate. Okay. Now, there are certainly some very, very smart mathematicians who figured out, well, how do we calculate some values for Markov chains that aren't, or sorry, for queuing systems that are not Markovian? Okay? And we call these general arrival processes or general service processes. Okay. So again, more formally, it's worth talking about the metrics that we're going to care about here. And typically, we use the following notation: WQ, W, LQ, L, and rho. Okay, so these are sort of the fundamental metrics that we're going to use. WQ is how long people wait in line. W is how long they wait in the system. Okay, so that includes the time waiting in line and the time being processed by the customer, or by the server, sorry. L of Q is the number of entities in the queue. while L is the number of entities in the queue, but also the number of people that are actually being serviced at that time. Okay. And finally, rho is this utilization. Okay. Be careful about rho. The rho we talk about in this class is going to be a little bit different than the rho we talk about in stochastic. So just be a little bit careful about that. All right. So queuing theory, the whole branch of mathematics, what they let us do is folks worked out equations to calculate these quantities based on given values of lambda and mu, and also see the number of servers that you have in your system. Okay? So if you were to tell me, hey, we get 5 customers per hour at my McDonald's, and I can service 10 per hour, right? Or each cashier can service 10 per hour and I have 2 cashiers, I can tell you how long each person is going to have to wait on average. Yes?
Yes. How do we calculate utilization?
We'll get to that. Yes. Okay. So, if we think back to our tables, we can think about, well, how do we calculate the average time in queue, right? This WQ. Well, you take the amount of time each person waited in the queue. So if you have 100 customers, you add up that value and then you divide by 100. Okay? But in theory, you want to do this for an infinite number of people, right? So that's more or less how we take this limit to infinity. Right? Similarly, we can do it with waiting in the system. And essentially what this is doing is this getting us a steady state average. So what do we mean by steady state? We normally talk about systems existing in 2 different modes. What's the other one? Transient. Transient. Is that how you spell transient? Okay. So let's say my McDonald's is closed. Okay. And what I'm going to plot here is the number of customers in line. Okay. And right here it's 7 a.m. when I open. Okay. Let's say entering system. Okay. So before 7 a.m., nobody enters into my system, and the number of customers, 0. Okay. Right when I open at 7 a.m., maybe there's a customer there, maybe there isn't. But what happens is customers start to fill in, and they enter and leave. And so this part where my system starts getting filled up with customers is referred to as transient. Okay. Now, let's say after an hour or 2, things start to even out, and I get a steady flow of customers going in and leaving. At that point, the number of customers in my system will sort of bounce around some average point. Okay. This part here is sort of the steady state. Okay? Right. So a lot of times when we talk about systems, the transient is whenever we have a change and our system is loading up. Not only does it load up in the morning, right, it comes down at night. Right? So the closing process is also a transient. Okay? So Publix is very nice. They don't kick you out of the store at 10 o'clock, right? Let you continue shopping till 10:15. And so even on the other side, you see it sort of go down. Okay? And this is a transient. Okay? But the steady state is where you sort of have this regular flow. It can be a little bit random, that's fine. But it's going to have sort of the steadiness of it. And so when we talk about these averages, that we take the limit as n goes to infinity, what we're assuming is that there's going to be a steady state average. That we don't have some weird transient going on. But after averaging enough customers in, this value W and WQ will reach a constant value. So let's say this was 10 p.m. and this was a McDonald's. Do you think this would be a realistic plot of how many people are in a McDonald's over a day?
No.
So yeah, it peaks at a few times. So there's two key times that this will probably peak, right? Lunch, dinner, breakfast. Okay? So more realistically, actually, let's do this. So there's a neat little trick. I love Chick-fil-A. Right, who doesn't? Oops. Come on. Hey, where'd this go? Not enough data. There we go. Okay, I love these graphs. Okay. So, what we see here is Google sort of tracks everything you do in life. Right? And so they can kind of keep track and estimate how many people are at Chick-fil-A because we're all walking in with our Android phone. And they track you every day of every second of your life. Okay? And so we can actually see this ramp up in the morning and then it comes down. And then between like 11 and 3, we see a surge in customers, right? And then from 3 to, 5 or 6, actually it's pretty steady, right? From 3 onward to about 7 or 8. Okay. There's a little bit of fluctuation there, but it looks pretty steady, okay? So a lot of times what we do when we build simulations is we'll say, let's simulate the lunchtime rush, and we're going to assume that the rate of customers coming in is steady. Okay, it might have some randomness, but we're going to assume steady state. Likewise, we can say from 3 o'clock to 8 o'clock, the rate of customers coming into a Chick-fil-A is more or less on average steady. Okay. Now that certainly isn't true from what, like 8, 9, 10? This is certainly a transient state from 7 o'clock onward, right? Because the number of folks that are coming into the restaurant is decreasing with time. Same thing in the morning, right? It's sort of increasing with time every hour. So we have a transient there. Okay? But we can sometimes focus in on an hour or two, right? So we could say from 12 to 2 o'clock, it looks like the amount of people coming in every hour is about the same. Okay, why not? You just have to be able to defend that statement. Okay, so again, we break up portions of our simulation into steady state and transient phases. Now, all these equations that we're going to talk about in queuing theory have to do with the steady state portion. Okay? So, in a similar way that we can calculate wait times, we can calculate the average length of the line. And so what you can do is you can look at every instant of the day and calculate how many people are in line, and then divide by the total number of time that you looked at, and that will give you the average number of people in the queue and the average number of people in your system. Now, the coup de grace are basically all the equations that folks worked out to calculate. And so the first thing that we start off with is we use this value rho here, which refers to the utilization of our server. Okay. And what it says is the utilization of the server is given by the arrival rate of customers coming in divided by the total service rate. Okay, so mu is the service rate for one server, but if I have 5 of them, so let's say each cashier can process 10 customers per hour, okay, then the total service rate, if I have 5 cashiers, is 5 times 10. So sort of the little toy example. Okay. Okay. So let's say customers come in with the rate of lambda equals 10 customers per hour. All right. I have 5 cashiers. All right. And maybe they can process, we'll say 8 customers per hour. Okay. So this 8 customers per hour refers to each of the cashiers. So the utilization then is given by lambda over C times mu. Right. So we can fill that in. 10 divided by 5 times 8. So what is that? 10 over 40? 1/4. Okay. So 25% of the time, or sorry, the utilization of my system is about 0.25. We do need to be a little bit careful about whether we're referring to an individual server or the system on whole. Okay, so, but usually, when we talk about utilization, this is the equation that we're referencing. Okay. All right. So when I have that row, that utilization, I can start calculating a whole bunch of other values that folks sort of worked out the math for. So one of the first things that we can figure out, and again, actually I should be specific, this is the utilization of the system. Okay. All right. So one of the first things people figured out is they said, well, can we calculate the probability of an empty queue? Right, so nobody's in line. And so it kind of makes sense that if your system's only utilized 25% of the time, then 75% of the time it's not being utilized and nobody's in line. And so that's why the probability of an empty queue is 1 minus rho. Okay. So that's nice and easy. Again, folks worked out some calculations and they said, well, we can calculate what the average length of a line is. And they worked it out to be rho squared divided by 1 minus rho. If we want to include the people in line, or sorry, who are being processed, so LQ is the people waiting in line, L is the people not only waiting in line, but being serviced, then it's rho over 1 minus rho. Similarly, we have equations for W, Q, and W. You sort of plug them in and get your values. Okay. Now, these equations here assume that you just have one server. If you have multiple servers, so like the example of the airport, in that case, use these equations here, and you sort of got to work through the math, right? Sort of plug in each other. Right? The interesting part when you calculate these equations, no matter what, you can see that LQ and WQ depend on this probability of 0, P0, that you have 0 people in the queue. So that means in order to calculate how many people on average are waiting in line, you're going to have to calculate this big ugly equation up there. Okay. So this is not an algebra class, right? So you guys are going to have to learn how to take powers and summations on your own. I'm sure Jorge or somebody will post some example problems. No?
They're not going to work into that.
Okay, they're not going to go into that detail? Okay. All righty. It's fine by me. Okay. All right. So these are the basic set of equations that we use when we're calculating performance metrics for a queuing system. Okay. All right. And again, I think these will be posted online. Really, I think these are the most important ones that I always had my students memorize, right? Or they should be able to recall pretty quickly. I don't think there's any expectation that you would ever memorize the equations on the right. I think they're a bit more complicated, right? But certainly you should memorize this. That's very important. Okay? All right. So one of the most useful equations in queuing theory is called Little's Law. And what it does is it relates the amount of time people wait in line with the average length of the line. Okay? And these are mediated through with lambda. Okay? So why is this useful? Okay? So we can understand why it's useful by looking at these equations here. Right? So let's say I gave you WQ and lambda, and I asked you, what is it? Sorry, what did I say? Let's say I gave you LQ and lambda. And I said, I want you to calculate WQ. Well, one thing you could do is calculate this figure of the equation right there. The other thing that you could do is just use Little's Law. You could say, hey, you gave me LQ and lambda. I could just solve for it by taking LQ and dividing it by lambda. It's awesome. Okay. Not only does this work for the queues, this works for the system as well. So how long did it take to be processed as well, right? So it's not just the queue, it's the overall queuing system, which is very, very cool. Right? Not only that, the neat part about Little's Law is that it doesn't even require the assumption of the Markov property. So whether your arrival rate is exponential or not, whether your service rate is exponential or not, these equations will always work. Right? And that's part of the power and amazingness of what is Little's Law, is that we can relate the length of a line of a queue with how long people wait, as long as we know the average rate at which people come. Now, there is one assumption that needs to be satisfied with this system. And actually, in fact, all the equations we worked with. Okay? So let's sort of do a little thought experiment here. Let's say, I'm working at McDonald's again, or Chick-fil-A. I love Chick-fil-A, all right? And I get 10 customers per hour, right? And I'm working by myself, right? Or maybe I'm working gas station, right? By myself late at night. I get 10 customers per hour, and I can process 20 customers per hour. Okay. Am I going to have a problem doing my job? No, because I can process more customers than are coming in. Okay, that's good. Now let's say lambda was 22 customers per hour, but I could still only process 20 customers per hour. What's going to happen? Yeah, the key is not only going to be really long, but if this system runs forever, what's going to happen to the length of that queue? Besides being, what's longer than long? Infinity. Okay? So if we pretended that this, let's say my gas station never closed, and we kept 22 customers per hour and 2 customers per, I could process 20 customers per hour. Every hour, how many more customers do I have in my system? I have 2, right? So in the first hour, I have 2 extra customers I can deal with. In the second hour, I have 4, right? In the third hour, I have 6. In the 1,000th hour, I have 2,000. In the 1,000,000th hour, I have 2 million. Okay? That line is just going to keep getting longer and longer and longer and longer. Okay? Why is this important? Well, Little's law makes the assumption, and it has the requirement, that lambda is strictly less than c times mu. Okay? So let's call this your processing power is greater than the arrival rate. Or you could call it your processing rate, doesn't matter. Okay. So this is a requirement. Not only is it a requirement for Little's law, it's a requirement for all these equations. So before you use any of these equations, calculate what lambda is and compare it to c times mu. Or, the other thing that you could do is you could say, well, we could look at the utilization and check, is that less than 1 or not? If your system utilization is less than 1, then you can use any of the equations. Right? But if your system is being utilized at more than 100%, then your system is unstable. Okay? And in fact, if mu is equal to 1, so let's be a little bit more explicit. So let's say mu is less than 1. We call that stable. All right, strictly. If it's greater than or equal to 1, it will be unstable. Okay? Even if you can process equally as quickly as they come in, your system is unstable. Okay? So just keep that in mind. Okay. So here goes a good example of Little's law, and I actually really like it because it demonstrates how Little's law can be used in sort of odd situations. Okay? It doesn't have to be a standard queuing system with 1 server or 2 servers, right? Working at an airport or McDonald's, something like that. It can be something much more complicated. So in this case, what I'm talking about is a university as a queuing system. Right? So in our university, so how many, well, I think there's a pretend university. Every year, we accept 5,000 students. Okay? In an ideal world, how long is a student waiting in that system to graduate? 4 years. Okay? And so what we can do is actually use Little's law, right? So we know L equals lambda times W, yeah? Okay. And that will tell us the length or the number of people that are in our system. So in this case, it's going to be 5,000 times 4, and that's equal to 20,000. I know I'm writing exactly what's here. But the point is, what does this 20,000 refer to? That's the number of people in the university. Okay. So I don't know what UCF looks like. Does anybody have any idea? Okay. So actually, we can figure this out, right? This is a good example. So we know we're now pushing 70,000, believe it or not. So we're at 69,000, I think, at the last measure. Okay. So why don't we calculate how many people are accepted per year? How long do you think it takes for the average person to graduate from UCF? 6. It might be that high. So I'm going to go with, how about 5.5 years? Okay. All right. So we could apply Little's law and take 69,000 and divide by 5.5. And what that would tell us is, on average, how many people we're accepting into UCF each year. Oh, 5.5. So about 12,500. Okay. So where is this calculation a little bit off? What? I'm making a couple of key assumptions here.
All students stay for a year. He drops out.
It's close. It's related to the time people spend here. 5.5 is average years to graduate. How many of you guys are transfer students? I would expect about half the class. How would you feel about staying 5.5 years here? Yeah, you already did your 2 years of time or 3 years of time at your junior college. Okay? So here I kind of made this odd assumption that everybody was what we call a FTIC, first time in college student. Right? So this is actually quite inaccurate. But it actually ends up being probably pretty close. You probably do accept around 12,000 students a year. So anyways, Little's Law, very, very cool stuff. Okay, so I think I got about half an hour. Okay. So there are, I'm probably not even going to spend any time here. The real fun part of queuing theory starts coming up when you start having non-Markovian assumptions. So you might get an exponential arrival rate, but the time it takes to be serviced might not be exponential. It might be normal, it might be uniform, it can be anything. And in fact, people have worked out the equations for what we call an NG1, right? And a GM1. Very hard. I'm going to assume before you guys not covering this. Okay. I tried to do it, and so many people got these problems wrong, so I don't blame you. Probably best to just sort of block it out of your head. But it is worth thinking about, because look at this one equation, right? Like, in order to calculate the waiting time here, it's 1 divided by mu times 1 minus z, where z is some crazy integral of the, what is that? The average time between arrivals. Okay? How many think you could calculate this for a normal distribution or something very, very low? And this is half the reason why we do simulations. Okay? We have a bunch of equations that tell us how long people are going to wait in line or wait in a system, assuming we have steady state, exponential arrivals, and exponential service times that remain constant over the day. All right. Let's look at Chick-fil-A. Does the arrival rate of customers stay constant over the day? It's going up and down, right? We're getting surges at lunchtime and surges around 9 a.m. You know, folks get their milkshake in the drive-thru or the little sandwiches, right? The biscuits. Okay. This is one thing that simulation can handle very well, while queuing theory struggles with if I asked you to simulate over a day. Okay. Queuing theory might tell you, okay, what's happening maybe in an hour or two, right? Assuming, making a lot of assumptions, but in simulations you can break a lot more assumptions. Okay. So that's something to keep in mind. Okay. All right. So at some point, nobody really cares about a single line and a server. People like studying more difficult problems. And the prototypical example in industrial engineering is at hospitals. And so people started asking, well, could we use queuing theory to understand a more complicated system where we have people that arrive, right? Maybe according to some Markov process. They sign in, right? If they can't sign in because they're like, seriously hurt, then they go straight to the trauma room, right? So maybe 10% of the people who arrive to the hospital go to the trauma room, 90% go to registration, right? They wait in registration, right? Everybody who went through registration then goes to an exam room. After the trauma room, these folks go to the treatment room. Certainly, you can imagine this might be incomplete because some folks from the exam room might actually, get examined and they go, hey, you have bacterial meningitis. And guess what's happening? They're going there, right? Or something like that. But with cueing theory, we can still understand what happens with these more complicated cues, right? So here we have one cueing system. Here we have another, and another, and another. Okay? And so we can start asking questions. Is there a way we can understand if a person arrives, how long will it be till they exit on average? And we can actually calculate these values. But in order to do that, we have to make a few assumptions. Okay. First, we're going to assume all our arrivals are exponential. And so this is that Markov process that we have all the three equations for. Also, all our service times are exponential in IIT. Again, this is so we can use those nice and easy equations in that table. Okay. The other assumption that we're going to use is we're going to assume that the capacity for the exam room, the registration, the sign-in is infinite. Again, so we can use our pretty equations. Right? So what you're seeing here is half the reason why we do simulations. Because in order to calculate how much time a person's going to spend on average in this emergency room, I have to start making assumption after assumption after assumption after assumption. But we can still do that. So the reason why we sometimes do these hand calculations is because they give us a basic understanding of what's going on and what sort of values to expect. So if we satisfy all these properties, and usually in this class we'll assume that they're true, or you'll be told that to assume that they're true, then we call this a Jackson network. Okay, and this is a very special type of network. Okay. With these properties of the Jackson network, we can couple it with two other properties that are closely related. One is, the first one, what goes in must go out. Okay? So, in a perfect world, 5,000 students enter college, 5,000 students leave college. You don't have one person who just stays in college infinitely. What goes in must go out. That is only true when lambda is less than c times mu. So again, this is a stability requirement. Okay. All right. So the other property that's related to Jackson networks, it's that if we look at rate splitting, splitting occurs according to the probabilities. So what do I mean by this? If we have 100 people per hour going into the queue, and 30% are going to go towards triage, then that means 30 people per hour are going to go to triage. Right? Maybe 10% will leave directly. They'll walk in and then walk out. Right? So then that means 10 people per hour will be taking this path. And so this fractional representation makes sense, right? You assume that the randomness keeps sort of averages out in the steady state. Okay? And so the rates that go out in each direction are in proportion to the probabilities. All right. Okay. So let's say I wanted to calculate how much time do I have? 10 minutes. Okay. I think we can do something in 10 minutes. Okay. Let's say we wanted to calculate how long it takes for a person to go through the system. Okay. So in order to do that, we have to calculate what is the wait time for the sign-in, what is the wait time for the registration, what is the wait time for the trauma room, the wait for the exam room, and the wait for the treatment room. Okay? Now the hard part is, how do we calculate all these? Well, first, how do we calculate them? Okay, so for the sign-in, it's pretty straightforward. We can just use our equation. Let's see, do I have it? Did anybody write it down? See, I should remember this. 1 over mu, 1 minus rho. 1 over mu, 1 minus rho. 1 over mu, 1 minus rho. 1 over mu. Okay. So we're going to give you mu for the sign-in. Okay. And you can calculate rho. So now you have W sign-in. That's fine. Okay. Okay. So if we get 1 arrival per hour going into the sign-in, actually, let's make a different assumption. Let's I don't know why I did that. Let's say I have 100 customers per hour going into my sign-in. What fraction of those arrivals are going to go towards registration? 90, right? So I'm going to have lambda into the registration is going to be 90. Well, lambda into the trauma room is going to be 10. Likewise, how many are going to go, what's the rate into the exam room? 90. Oops. All right. If 90 go into the exam room, how many are going into the exit? Say it in words. 0.4 times 90. Anybody know what that is? $36? All right. So how many are then going to the treatment room? 90 minus 36? Is that 44 or 54? 54. Okay. But we got an issue. So we have folks from the trauma room going into the treatment room. So what is the total lambda into the treatment room? 64. Okay. All right. So what we've done is we've calculated the lambda into each one of the servers. Okay. And we're a little bit careful here with the treatment room because we see that the lambda going into the treatment room is 54 customers per hour from the exam room and 10 customers per hour from the trauma room. And so we have a total of 64 customers per hour going into the treatment room. All right. So how would I calculate this is sort of an advanced question. How would I calculate the average time that a person spends in the hospital? Yeah, you could do that. I think that's the best way, actually. No? You want to do that? That's what I would do. So, I'm going to sort of read back what the gentleman said. The gentleman said, you can look at all the different paths that people take through the system. Okay? So let's sort of look at these 3 different paths. All right. Can I copy this? I'm going to erase all this stuff. Okay, so we have a few different paths through the system. One path, folks go this way. So there's path 1. Another path, folks go this way. And then finally the third path, we have folks who go that way. For each one of these paths, the time that they spend on it is the average time added up, right? So for the space path, we add the average time in sign-in, plus the average time in registration, plus the average time in exam room, plus the average time in the treatment room. And that will give us the time for, let's call that number, we'll call that number 1, okay? This will be number 2, and the green will be number 3. So what you can do is you can calculate the time for number 1, the time for number 2, and the time for number 3. That doesn't quite get us the answer though. We need to know what fraction of folks take the purple path, and what fraction of folks take the space path, and what fraction of folks take the green path. Alright, so pretty easily, we might be able to tell what fraction of folks take this green path. Does anybody know? 10%. Yeah. Right. So that means 90% of the people take the purple or the space. Okay? So what fraction take the purple? Oh, 36. Yeah, we got the nice number, right? 30.36. And you can just get that from 0.9 times 0.3, or you can look at what the rate was going through this particular segment. Right? Likewise, we can get the probability that somebody takes this space path. Right? So if I have all the times, then the average time in system, so I'll just put a bar, is equal to the probability that you take that first path times t1, plus the probability you take the second path times t2, plus the probability you take the third path times the amount of time it takes to go through that third path. And again, I think P3 was equal to 0.1, P2 was 0.36, and this last one was what? 5.4? 5.4. And all you need to do, not all, but you need to calculate the times it takes along each path. So you're going to calculate for T1, it is the time at sign-in plus the time for registration plus the time for the exam. Okay, T2, sign-in, registration, exam room, treatment room, and finally T3 is sign-in, trauma room, treatment room. Okay? You just apply that question. Of course, if you have more paths, then you have more T's that you need to calculate, more probabilities. But that's what you're doing. So I'm going to say one more thing. If you could, I got one more minute, so I'm going to use that minute. So the types of question that we're going to start asking in this class is, do I have enough exam rooms? How big should my waiting room be, right? What if 10% more patients arrive, right? What if there's some sort of emergency, right? And I get 100 patients all at once. What happens? Should I be treating folks first come, first serve? Probably not in a hospital, right? If I apply a different policy, and let's say if anybody waits more than 1 hour before getting treated, bad things happen, right? These are the types of questions we can ask and answer. Now the issue is, with queuing theory, we have to make all these assumptions, okay? The world is random. The world follows weird distributions. It's not what we always think it is. And at least with simulation, we don't have to make all the assumptions with queuing theory. And so really, part of this class, and the reason why we go through queuing theory, is so that you understand the limitations, but you know, okay, order of like approximation what things look like. And then you compare it with your simulation, see how it works out. Okay, guys, thank you very much. Have a good one.